In 2012, in a short paper in the Astrophysical Journal Letters, an astrophysicist at Yale University named Nikku Madhusudhan and his collaborators proposed something genuinely strange. They proposed that a planet 41 light-years from Earth around a star you can just barely see with the naked eye on a dark night was made, more than half by mass, of carbon. The crystalline form of carbon, diamond. The planet is called 55 Cancri E. It orbits its star in 17 hours and 44 minutes. Its day side sits at about 2,400 degrees Celsius. It is 8 times the mass of Earth and twice its radius, and the density that came out of the measurements was consistent in 2012 with a rocky world that was on the inside, nothing like our own. When the press picked the story up in the days after the paper was published, the diamond planet was reported as worth, in pure mineral value, more than 26 nonillion dollars. That is 26 followed by 30 zeros. A number, by the standard of human commerce, that has no meaning at all. But here is what almost nobody who saw the headline went on to read. The diamond planet, when astronomers measured its host star's chemistry more carefully over the next decade, turned out to be quite a bit more complicated than the original paper had suggested. The diamond, by the standards of the current evidence, is probably not there. What is actually there 2 decades after the planet was first discovered is a question we are still working out. If you find that as fascinating as I do, hit subscribe. Pour yourself something warm, get comfortable, and settle in. Because tonight we are going to walk slowly through the strange and quietly beautiful story of a planet we thought was made of diamond, of how that hypothesis came into being, of what made it both plausible and ultimately fragile, and of what we now, very tentatively, think might actually be there instead. Now, let's ease into it. Part 1. Part 1. The little planet right next door. 55 Cancri E is, by the standards of exoplanet astronomy, very close to home. 41 light-years is a distance that, in cosmic terms, is essentially next door. There are, in the catalogue of confirmed exoplanets, only a handful of well-characterized worlds closer to us. The host star is bright enough that, on a dark, moonless night in a region of sky reasonably free of light pollution, you can see it with your naked eye. It is in the constellation Cancer, the crab, which lies between the much brighter Leo to its east and Gemini to its west. Cancer is one of the dimmest constellations in the zodiac, and 55 Cancri, with a magnitude of about 6, is right at the edge of what an unaided human eye can resolve. If you know exactly where to look on a clear night in dark conditions, you can find it. Most people, even those who know the sky reasonably well, walk right past it. The star itself, when astronomers catalogued it in the 19th and 20th centuries, was assigned a number in several different stellar catalogues. The 55th star of the constellation Cancer in Flamsteed's catalogue, hence the name 55 Cancri. Various other designations exist. The star is part of a binary system. There is at a separation of about 1,000 astronomical units, which is about 25 times further than Pluto is from our Sun, a small red dwarf companion called 55 Cancri b. The companion is so dim and so far that it has very little gravitational influence on the inner system. For our story, we can treat 55 Cancri A, the brighter star, as effectively a single star. 55 Cancri A is, in many ways, a near twin of our own Sun. It is slightly older, perhaps 8 billion years old, where our Sun is 4.5. It is slightly cooler, with a surface temperature of about 5,200 degrees Celsius, where our Sun is about 5,500. It is slightly less massive at about 95% of the Sun's mass, but it is, by every important metric, the same kind of star, a G-type main sequence star, the kind around which, if planet formation works the way we think it does, you would expect to find planets that resemble in their broad outlines the planets of our own solar system. And that is, more or less, what astronomers have found around 55 Cancri A, 5 planets, in orbits that range from extremely tight to comfortably wide, with masses ranging from a few times Earth's to several times Jupiter's. The system is, by exoplanet system standards, a fairly normal one. The constellation Cancer itself in the human imagination has a long history that is worth a brief pause. The Greeks associated the constellation with the giant crab that, in the myth of the 12 labours, was sent by the goddess Hera to harass Heracles during his battle with the Lernaean Hydra. Heracles in the story crushed the crab beneath his foot, and Hera, to honour its service, placed it in the heavens. The Babylonians, much earlier, called the same patch of sky Alul, which appears to mean some kind of crab or crayfish. The Egyptians associated it with the scarab beetle, the symbol of resurrection and renewal. Almost every civilization that watched the sky carefully built a story around this small, dim cluster of stars between the much brighter patterns of Gemini and Leo. For all of those civilizations, 55 Cancri was just one more faint star in a faint constellation. Nobody saw it as remarkable, nobody attached a story to it specifically. It was, in every star catalogue from antiquity to the early 20th century, a number among many. The fact that this otherwise unremarkable star would in our generation host one of the most intensely studied small planets in the catalogue is, in some sense, an accident, a combination of brightness, proximity, and orbital geometry that put it in the right position for the kind of techniques that emerged in the early 21st century. The civilizations that drew the crab in the sky did not know what was around any of the stars in the pattern. We, in our generation, are the first to know that around one of the dimmer ones there is a small, dense super-Earth that does in 17 hours what Earth does in 365 days. The exception, the planet that breaks the otherwise unsurprising pattern, is the innermost world. The little b for the catalogue convention says first found, but in 55 Cancri's case, the planet we are talking about tonight, the innermost one, was actually the 5th to be found. So by historical convention it is named 55 Cancri E, 5 planets in the system, the 5th letter of the planetary naming convention, the innermost orbit, a small, dense, hot world in an orbit so close to its star that the year is shorter than a human work shift, with a day-side temperature that would melt aluminium, and an interior structure that, when astronomers first measured it, did not quite fit any of the easy categories. Here is the thing that made 55 Cancri a target of such intense study. Not just the orbit, although the orbit was unusual, not just the temperature, although the temperature was extreme. The thing that pulled astronomers' attention to this particular world and kept them on it for the better part of 2 decades was that its bulk density implied an interior composition that, in 2012, no model in the standard textbook quite explained. The planet was a puzzle. The puzzle was specific. The puzzle had, in the form of the diamond hypothesis, an extraordinary candidate solution. And whether or not the diamond solution turned out to be right, the question of what 55 Cancri E is actually made of has, ever since, been one of the more interesting open questions in the field. We will get to the diamond. First, we have to look at how anyone found this planet at all. Part 2. How we found a planet 17 hours from its star. The discovery of 55 Cancri A was, in some ways, a slow and indirect process because the planet's existence was inferred years before it was directly confirmed. The first hints came in 2004 in a paper led by an astronomer named Barbara MacArthur at the University of Texas at Austin. MacArthur and her collaborators were using radial velocity measurements taken with the high-resolution spectrograph at the McDonald Observatory in West Texas to study the wobble of 55 Cancri A as it was tugged on by the gravity of its known planets. The technique relies on the fact that when a star has planets, the star itself does not sit perfectly still. The mutual gravity of the planets and the star pulls the star, very slightly, in a small wobble around the system's center of mass. The wobble shows up in the star's spectrum as a small, periodic Doppler shift, which a sensitive spectrograph can detect. The Doppler shifts, accumulated over years, give a record of how the star is being pulled, and from that record, the orbits and masses of the planets can be reconstructed. By 2004, 3 planets were already known around the star. MacArthur's team was looking for residual signals in the radial velocity data after subtracting the contributions from the known planets, in case there were any additional, smaller worlds in the system that had been missed. There was a residual. It was small. It had a period of just under 3 days. The signal was, at the time of detection, at the limit of what the instrument could measure, and the team announced it cautiously. They proposed a Neptune-mass planet in a roughly 3-day orbit very close to its star. They named it 55 Cancri E. Here is the part of the MacArthur paper that, in retrospect, is more remarkable than it looked at the time. The team made the detection by combining radial velocity data with very precise astrometric measurements from the Hubble Space Telescope's fine guidance sensor. The astrometric data, which measures how the star's position on the sky shifts very slightly as the planets pull it around, gave them an independent constraint on the planetary system. By combining the two techniques, they were able to extract a signal that neither technique, on its own, could have pulled out cleanly. The discovery was, in some sense, an early example of the kind of multi-technique combined analysis that has, in subsequent decades, become standard in the field. MacArthur's team was, in 2004, doing in 2004 what would, by 2015, be done routinely by many other groups. They were ahead of their time. MacArthur herself had a long career at the McDonald Observatory, the optical observatory at the University of Texas at Austin, located on a high desert ridge in the Davis Mountains of West Texas. The observatory has been in continuous operation since 1939. It is, by the standards of optical astronomy, a venerable institution. MacArthur joined the staff in the 1970s and, over a long career, made contributions to many areas of stellar and planetary astrophysics, including the precise measurement of stellar masses and the detection of low-mass companions. The 55 Cancri E detection was, in some sense, the kind of result her career had been preparing her to make. A small signal, at the limit of detection, in the residuals of a multi-planet system, requiring careful combined analysis. The kind of work that does not on its own make headlines, but that fills in the bricks of the scientific catalogue, one careful measurement at a time. The detection was published in 2004, and although the announcement received a modest amount of press, it was not, in itself, treated as a particularly remarkable result. The field, by 2004, was finding planets at a rate of dozens per year. Another close-in Neptune was, on its own, not a sensation. There is a small but interesting detail about how this kind of detection feels from inside the field that is worth mentioning. The MacArthur paper announcing 55 Cancri E in 2004 was, by the standards of the time, a routine multi-author result. The lead author was a senior staff scientist. The collaborators were experienced colleagues. The paper went through normal peer review, was published in the Astrophysical Journal, and was, in the small community of researchers working on the 55 Cancri system, accepted as an addition to the catalogue. There was no press conference. There was no front-page coverage. The paper was, in some real sense, an accumulation of the kind that science, on most days, consists of. A small new result slotted into the larger picture with its appropriate caveats noted. The trouble was that the original detection was wrong, not the existence of the planet, which turned out to be real. The orbital period, the 3-day signal that MacArthur's team had identified was, by 2011, demonstrated by independent observations to be incorrect. The actual period was much shorter. It was, in the end, about 17 3/4 hours. The planet was much closer to its star than the original detection had indicated, and it was, correspondingly, much hotter. The mass came out lower as well, somewhere around 8 times Earth's mass rather than 17, and the planet, on the new measurements, was no longer a Neptune. It was a super-Earth, a small, dense, rocky world, in an orbit so tight that it completed an entire revolution in less than a single Earth day. The transit detection, which confirmed the new orbital parameters, was made in 2011, almost simultaneously by 2 different teams. One was led by an astronomer named Bryce Olivier Demery at the Massachusetts Institute of Technology. The other was led by Joshua Wynne at MIT and his collaborators using the MOST satellite, a small Canadian space telescope dedicated to high-precision photometry. Both teams, working independently, observed the dimming of 55 Cancri A on the predicted transit schedule, and both teams confirmed that the planet was real, in a 17-hour orbit with a radius of about 2 Earth radii. Here is the detail that made the transit detection so important. Once you know the radius of a planet, in addition to its mass, you can compute its density. And once you have the density, you have a strong constraint on its composition. A purely rocky planet like Earth has a density of about 5.5 grams per cubic centimetre. A water world has a much lower density, perhaps 2 or 3. A gas-dominated planet has a much lower density still. The density of 55 Cancri A, when the new measurements were combined, came out at about 6.5 to 7 grams per cubic centimetre. That was higher than Earth's, higher than the density of any of the rocky planets in our own solar system, higher than any reasonable water-dominated world. What kind of planet has a density like that? In 2011, when the measurement was first made, the answer was not entirely clear. The simplest model was an iron-rich super-Earth, with a larger fraction of iron than Earth has. That model worked, more or less, but it required the planet to have an iron core that was roughly twice the mass fraction of Earth's iron core, which seemed slightly unusual. Other models were considered. None of them was particularly clean. The interior of 55 Cancri E, on its first thorough characterization, did not quite fit any of the standard categories. It was, in some sense, looking for a story. The story arrived in 2012, Part 3, the shortest year we know. Before we get to the story, it is worth pausing on the orbit, because the orbit is so unlike anything in our own solar system that it is genuinely hard to picture without spending a few minutes on it. The orbital period of 55 Cancri A is 17 hours and 44 minutes. Not 17 days, not 17 weeks, not 17 months, 17 hours, less than the length of a human waking day. By the time you finish breakfast on Earth, 55 Cancri A has, in its own system, completed a substantial fraction of an entire year. By the time you go to bed at night, it has finished one complete year and started another. By the time the week is over, it has had, on its calendar, 10 full years. The planet is, at this orbit, about 2.25 million miles from its star. That is roughly 25 times closer than Mercury is to our Sun. The orbital velocity, given the gravity of the host star, is enormous. The planet is moving at about 240,000 miles per hour, which is roughly 33 times faster than Earth moves around the Sun. From a vantage point on the planet, if such a vantage point existed, the host star would not look like a familiar yellow dot in the sky. It would look like a vast, glowing orange-yellow disk, taking up about a quarter of the sky in its angular extent, about 60 times wider in apparent size than the Sun looks from Earth, far too bright to look at directly without instant blindness, far too hot to be near, in any conventional sense. The temperature on the day's side of 55 Cancri A, where the star is permanently overhead, is about 2,400 degrees Celsius. That is hot enough to melt aluminium, hot enough to melt iron, hot enough to melt almost any rock you might think of. The night side is much cooler, by perhaps 1,000 degrees, although it is still, in absolute terms, hot enough to keep most metals liquid. The planet, like WASP 12b in our previous story, is almost certainly tidally locked, with one side permanently facing the star and the other permanently facing away. There is no day-night cycle, there is just the day side and the night side and a thin terminator strip in between where the temperature transitions from one extreme to the other. Let me sit with that for a moment. The whole planet is at a temperature on its day side where the rocks themselves would not be solid, where the surface, if there is a surface in any conventional sense, would be liquid. There is a calculation that, the first time you encounter it, is hard to absorb fully. The amount of energy that 55 Cancri E receives from its star per unit area is about 2,500 times the amount of energy that Earth receives from the Sun. Per unit area, 2,500 times. That is the difference between standing in normal sunlight on a summer afternoon and standing in the focus of a furnace specifically designed to vaporize metal samples. The energy density at the planet's surface is, by every measurement, sufficient to keep most rocks at temperatures well above their melting points, and the planet, in steady state, has settled into the equilibrium where the surface is, in fact, mostly liquid. It is not, importantly, an unstable equilibrium. The planet has been like this, almost certainly, for as long as it has been in its current orbit. Billions of years. The magma ocean has been sitting there under its star, breathing slowly, since long before any human civilization existed. Here is the thing that often gets lost in the discussion of magma ocean planets. The image of an ocean of fire, when you say it casually, sounds dramatic, it sounds catastrophic, it sounds like something that would have to be transient, like a recent volcanic eruption or a passing impact event. The reality is the opposite. The magma ocean on 55 Cancri A is the steady-state surface. It is what the planet looks like when nothing dramatic is happening. The eruptions, the volcanic vents, the variable hotspots are perturbations on top of the underlying calm of an ocean of liquid silicate that has been there, doing what oceans do for the entire age of the system. The drama in this picture is not the magma. The drama is the small variations on top of it. That last point is one of the more important features of the planet, and it is worth dwelling on. In our own solar system, every solid planet we have studied has a solid surface. Earth has continents, oceans, ice caps. Mars has rocky deserts, polar caps, ancient riverbeds. Mercury has cratered grey rock. Venus has a hot, dense atmosphere over a basaltic surface. None of them, even in the hottest places, has a surface where the rock itself is liquid all the time. Even Venus, the hottest planet in our own system, has a surface that, while hot enough to melt lead, is well below the melting point of silicate rock. The rocks on Venus are solid. The rocks on 55 Cancri E's day side are not. At 2,400 degrees Celsius, the silicate minerals that make up most of the crust of any rocky planet are, in their thermodynamic equilibrium, liquid. The day side of 55 Cancri A is, almost certainly, an ocean of molten rock, a magma ocean, not metaphorically, literally. The whole substellar hemisphere of the planet, the half permanently facing the star, is, by every model that has been done, a global pool of liquid silicate magma, possibly with islands of slightly cooler material near the terminator, possibly with a complex circulation pattern driven by the temperature gradient between the substellar point and the terminator, possibly with the surface itself flowing in slow currents at the speed of geological tides. That picture of a planet whose day side is a global magma ocean is the starting point for almost everything else we're going to talk about tonight. It is what makes 55 Cancri E so unlike anything in our own system. It is also what made the question of the planet's composition in 2012 so genuinely puzzling, because if the day side is liquid silicate, what is at the surface of that ocean? What is the chemistry? What, when the silicate boils off into the upper atmosphere, gets carried by the winds and then condenses again on the cooler night side? And what, beneath the magma ocean, lies in the deeper interior? These are not abstract questions. They have, in 2012, very specific answers, depending on what the planet's bulk composition turns out to be. And in 2012, the dominant answer to that last question, briefly, was diamond. Part 4. A density that did not quite fit. To understand why the diamond hypothesis was proposed in the first place, you have to spend a few minutes with the density problem. The mass and radius measurements of 55 Cancri E after the 2011 transit detection gave a bulk density of about 6.5 to 7 grams per cubic centimetre. That number, by the standards of planetary science, is constraining. It rules out a lot of possible compositions. It rules out immediately any composition dominated by light elements. The planet cannot be mostly water, mostly hydrogen, mostly methane. None of those would give a density that high. A water world the same size as 55 Cancri E would have a much lower density, around 2 or 3. The high density rules in, instead, dense, rocky and metallic materials. Iron, silicate rock, carbon. In its denser forms, possibly some heavier elements in the deep interior. The question, given the high density, is what proportions of these materials make up the bulk of the planet. The simplest comparison is to Earth. Earth's density of 5.5 grams per cubic centimetre comes from a mantle made mostly of silicate rock, with a density around 3.5, and a core made mostly of iron, with a density around 8 or 9. The silicate mantle accounts for about 2/3 of Earth's mass, the iron core for about 1/3. The proportions, when you do the math, give Earth's overall density. 55 Cancri E's density is higher than Earth's. By the same logic, the planet must have either a larger fraction of iron in its core or a different composition altogether. The simplest model, and the one most astronomers initially adopted, was an iron-rich super-Earth, a planet with a larger relative iron core and a thinner silicate mantle. By that model, the planet would have an iron mass fraction of perhaps 50 to 60%, compared to Earth's 30%. That would account for the density. The model was, in 2011, the consensus picture. But there was a complication. The iron-rich super-Earth model required the planet to have formed in conditions that produced a much higher iron-to-silicate ratio than Earth experienced. Possible, but not common. And there were other complications. The host star, 55 Cancri A, had been measured to have an unusual chemistry. Its abundance of certain key elements, when measured in detail, was not quite the same as our own Sun's. Specifically, the carbon-to-oxygen ratio of 55 Cancri A by some early measurements came out higher than the Sun's, possibly significantly higher, possibly above the threshold of 1 where, in standard planet formation models, things start to get strange. Here is the part that mattered. In planet formation, the carbon-to-oxygen ratio of the host star sets the chemistry of the protoplanetary disk that the planets form from. The CO ratio is, in some sense, one of the dominant compositional parameters of any system. It controls which solids condense at which temperatures, in which sequence, as the disk cools after the star's formation. It controls what kind of grains the planetesimals are built from. It controls, indirectly, what the rocky planets are made of, what their atmospheres look like, what their volatile inventories include. A small change in the host star's CO ratio from below 1 to above 1 produces a fundamentally different kind of solar system. Different planets, different chemistries, different geological possibilities, different conditions for life, if life is on the table. The CO ratio, in modern planet formation theory, is one of the most consequential numbers a star can have. If the CO ratio is below 1, which is the case in our own solar system, oxygen dominates. Most of the rock-forming elements end up bound to oxygen in the form of silicates and oxides. The planets that form are rocky in the way Earth is, with silicate mantles and iron cores. If the CO ratio is above 1, however, carbon starts to play a much larger role. Some of the elements that would otherwise bind with oxygen end up bound with carbon instead, in the form of carbides and carbon-rich compounds. The planets that form in this regime can be much more carbon-dominated than anything in our own system. Their interiors can include layers of graphite, of silicon carbide, and, at the right pressures and temperatures, of diamond. In 2012, with the high-density measurement of 55 Cancri E in hand, and with the early indications that 55 Cancri A might have an elevated carbon-to-oxygen ratio, Madhusudhan and his collaborators put 2 and 2 together. Maybe, they suggested in their paper, 55 Cancri E is not an iron-rich super-Earth at all. Maybe it is something nobody had ever seen before. A carbon-rich planet, a world whose interior, instead of being dominated by silicate and iron, is dominated by carbon in its various crystalline forms. A world whose mantle, beneath a thin outer crust, is, at depth, a layer of diamond hundreds of kilometers thick. It was a striking hypothesis. It fit the data, more or less. It made testable predictions about the host star's chemistry, about the planet's emission spectrum, about the way the bulk density should respond to refined mass measurements, and it captured almost immediately the popular imagination. Here is the chemistry, in slightly more detail, of how a carbon-rich planet would actually be put together. Carbon, in the deep interior of any planet, exists in different crystalline forms depending on the pressure and temperature. At the surface of a hypothetical carbon-rich super-Earth, where the pressure is comparatively low and the temperature is moderate, the dominant form would probably be graphite. Graphite is a layered black mineral made of stacked sheets of carbon atoms in hexagonal arrangement. It is, on Earth, what pencil leads are made of. It is soft, slippery, and conductive of heat and electricity. A graphite-surfaced planet would be, in some sense, a black world. The light reflected off it would be dim, in the way that coal reflects very little light. The colour, from outside, would not be cobalt blue, like HD 189733b. It would be much darker, almost black, with perhaps a slight reddish cast from the metallic chemistry beneath. Below the graphite surface, at depths of perhaps a few hundred kilometres, the increasing pressure would start to compress the carbon into a different crystalline form: diamond. The conversion of graphite to diamond on Earth requires pressures of about 30,000 atmospheres or more, and temperatures in the range that geologists associate with the upper mantle of a rocky planet. Both conditions would be easily met inside a carbon-rich super-Earth. By a depth of perhaps 500 kilometres, the carbon would be transitioning from graphite into diamond. By a depth of 1,000 kilometres, the conversion would be essentially complete. From there down, all the way to the iron core, the dominant material would be diamond. Here is a small detour worth taking because it tells you something about how unusual a planet-scale layer of diamond would be. On Earth, almost all of the diamond in commercial circulation comes from a small number of very specific geological deposits. Diamond forms naturally only at depths of roughly 150 kilometers or more below the Earth's surface, where the pressure and temperature are right for carbon to crystallize. The diamonds we mine reach the surface only because of a particular kind of volcanic eruption called a kimberlite eruption that brings deep mantle material rapidly to the surface. Without that very specific geological mechanism, the diamonds would stay buried and we would have no significant supply of natural diamond at all. The total mass of all the diamond ever mined in human history is, by the most generous estimates, somewhere on the order of a few thousand tons. That is, in cosmic terms, a tiny amount. A single asteroid of carbonaceous chondrite material crashing into Earth could deliver more carbon than the entire commercial diamond stockpile, several times over. That is the entire commercial diamond stockpile of human civilization, accumulated over hundreds of years of mining. A carbon-rich super-Earth in the strong form of the Madhusudhan model would contain something on the order of 10 to the 24 kilograms of diamond. That is A1 followed by 24 zeros in kilograms, or equivalently 10 to the 21 tons. That is 1,000 billion tons, the total commercial supply of human diamond multiplied by 10 to the 18 times. A factor of a quintillion, the number is so large that in any economic sense it is meaningless. The diamond, if it were there, could not be valued by any conventional commercial metric. The dollar figure that the press attached to the planet, $26.9 nonillion, was simply the current per carat retail price of diamond multiplied by the estimated planetary mass of carbon, ignoring the fact that no plausible market could absorb that much supply, and ignoring also the fact that no plausible technology could ever extract a meaningful quantity of it. The figure was a curiosity, not a real valuation. It captured imaginations because the number itself was unimaginable. It would not be, importantly, the diamond you see in jewelry. The diamond in a wedding ring is a single crystal, grown slowly under very specific natural conditions, then cut by a human jeweler into the faceted shapes that catch and refract light in the way that, on the finger of a person at a wedding, looks the way it looks. That is one specific kind of diamond in one specific kind of presentation after one specific kind of human processing. The diamond inside a carbon-rich super-Earth would be polycrystalline with grains on the scale of microns to millimeters packed against each other in a complex texture. It might be opaque mostly. It might have impurities of nitrogen, boron, or other elements that would tint it various colors. Naturally occurring diamonds on Earth, depending on their trace impurities, are sometimes blue, sometimes pink, sometimes yellow, sometimes brown, sometimes a deep amber. The pure white diamonds that dominate the jewelry market are, in the language of mineralogy, comparatively rare. Most natural diamonds on Earth have at least some tinge of color. The diamonds inside a hypothetical carbon-rich super-Earth, with the various trace impurities likely present in the deep interior, would almost certainly be colored rather than colorless. The deep mantle of such a planet, if it could be sampled in some hypothetical way, would not be a single uniform white. It would be, more likely, a complex tapestry of different shades, depending on which trace elements were present in which locations. The image of a planet with a uniform layer of clear, colorless diamond is, even within the hypothetical model, almost certainly not what the actual material would look like. It would, importantly, be under enormous pressure. The diamond at 1,000 kilometers of depth in a super-Earth would be at hundreds of thousands of atmospheres of pressure. The mineral might, at that pressure, behave in ways that we do not have a good way to test in the laboratory. Some of the predictions of high-pressure mineral physics suggest that, at sufficiently high pressures, diamond itself transforms into yet another denser carbon mineral, sometimes called BC8 or post-diamond, which has a different crystal structure entirely. The deepest interior of a carbon-rich planet might, on these models, be made of something even stranger than diamond. Let me sit with that for a moment. The interior of a carbon-rich planet, if such a planet exists anywhere in the galaxy, is a chemical environment that we have very little hands-on experience with. The materials, the textures, the behavior are at the edge of what laboratory experiments can replicate. Part 5. Here is where the diamond planet story begins. Here is where the story takes its iconic turn. The first thing that happened in the immediate aftermath of the 2011 transit detection was a flurry of theoretical activity. Several different groups working independently started fitting interior models to the new mass radius data. Some groups proposed iron-rich models, some proposed water-rich models, some proposed unusual silicate compositions. The interior structure of any rocky planet is, by the standards of the rest of physics, a hard problem. The temperatures and pressures inside a planet, especially a super-Earth, exceed what any laboratory can easily reproduce. The behavior of materials under those conditions has to be inferred from a combination of theoretical calculations, high-pressure experiments using diamond anvil cells, and astrophysical observations of objects whose interiors we can model. Each of these sources of information has its own uncertainties. Combining them into a coherent picture of what a particular planet's interior might look like is a delicate exercise. The space of plausible interior structures was, in 2011, genuinely wide. Almost any model that gave a density of around 6.7 grams per cubic centimeter with the right total mass would fit the bulk observations. The data did not, on its own, pick out a unique answer. It only constrained the answer to a band of possibilities. That is, in some sense, the point at which a hypothesis, like the diamond planet model, becomes useful. With the data so weakly constraining, the question becomes, what is the most physically plausible model that could produce the observed properties? Different groups, given the same data, came to different answers. Madhusudhan's contribution was to point out that, given certain assumptions about the host star's chemistry, a carbon-rich interior was a viable possibility that nobody had yet seriously considered. The hypothesis was, in this sense, an exploration of a corner of the parameter space that the more conventional models had ignored. It was good, exploratory science. The Madhusudhan, Lee and Moose's paper, which appeared in the Astrophysical Journal Letters in October of 2012, was titled, somewhat dryly, A Possible Carbon-Rich Interior in Super-Earth 55, Cancri E. The paper itself was technical. It worked through the chemistry of carbon-rich protoplanetary disks, the conditions under which silicon carbide and graphite would condense as solid grains in such disks, the resulting interior structure of a planet formed from those grains, and the predictions for how such a planet's mass-radius relationship would compare to that of an iron-rich rocky world. The paper was careful. It did not claim in its actual text that 55 Cancri E was a diamond planet. It claimed only that a carbon-rich interior was a possible model that fit the available data, and that the host star's elevated carbon-to-oxygen ratio supported that model. What happened next was a press cycle that the paper itself had not really invited, but which, in the small world of exoplanet popularization, was probably inevitable. Within days of the paper's publication, headlines began appearing in newspapers and on websites around the world. The Daily Mail in London ran a story titled "The Diamond Planet That's Worth $26.9 nonillion." The BBC ran a similar piece. Astronomy magazines followed. The estimate of the diamond's value, which was based on the assumption that a third of the planet's mass might be diamond, multiplied by the current commercial price of diamond on Earth, produced the dollar figure that captured the imagination. 26.9 nonillion is 26.9, followed by 30 zeros. The number is meaningless in any economic sense, because no amount of diamond on Earth, let alone 41 light-years away, could be sold without crashing the diamond market entirely. But the number was striking. The headline was striking. The diamond planet, as a popular concept, was born. There is a piece of context worth adding here, which is that Madhusudhan was, at the time, a postdoctoral researcher at Yale University. He had completed his PhD at MIT a few years earlier, working on exoplanet atmospheric retrieval techniques. The carbon-rich planet paper was one of several he was working on as he transitioned from postdoctoral work to a permanent academic position. He has since gone on to a distinguished career, including the Cambridge professorship, that by 2023 would put him at the centre of the K2 18b biosignature story I told in our previous evening's tale. The Diamond Planet paper, in the long arc of his career, was one paper among many. It got more press than any of the others. That is, in itself, a function of how science gets reported, not of how the science itself ranks the paper. Madhusudhan himself was, in the days after the paper, asked many times by journalists about the popular framing of the result. His answers in interviews were uniformly cautious. He emphasized that the paper proposed a possible interior, not a confirmed one. He noted that the host star's chemistry was uncertain and would need to be measured more carefully. He was clear that the diamond planet was a hypothesis, not a discovery. But the cautions in the popular telling did not quite stick. The image of an alien world made of diamond was, by the end of 2012, firmly established in the public imagination. Here is the thing about the Diamond Planet story that I find quietly remarkable. The hypothesis was, on its own scientific terms, a reasonable one. It fit the data. It made specific predictions. It identified very clearly what kind of follow-up observations would test it. The press coverage, with its dollar figure and its headlines, was a separate phenomenon, layered on top of the science. The science, when it was eventually tested, ended up walking the hypothesis back, slowly, over the next 10 years. But the hypothesis itself, in its original form, was good science. It was the kind of bold, testable, falsifiable proposal that good astrophysics is made of. Let me sit with that for a moment. The story tonight is not a story of scientists getting it wrong. It is a story of scientists making a careful guess, of journalists running with the most striking version of that guess, and of subsequent observations gradually revising the picture. That is, in some sense, exactly how the field is supposed to work. Part 6. What it would take for a planet to be made of diamond. For a planet to actually be made of diamond in the sense the Madhusudhan paper proposed, several specific conditions have to hold. It is worth walking through them because they tell you something about how planet formation works and about what the difference between a carbon-rich and an oxygen-rich world actually means. The first condition is that the host star's chemistry must include a high carbon-to-oxygen ratio. Our own Sun, like most stars in our local galactic neighborhood, has a CO ratio of about 0.55. There is roughly twice as much oxygen as carbon in the gas from which our solar system formed. That ratio is what gives Earth its silicate-rich crust, its oxygen-rich oceans, its carbon-poor interior. Most of the carbon in our solar system, in fact, ended up in the cooler outer parts of the disk, where it formed comets and primitive organic compounds, rather than in the inner rocky planets. For a planet's interior to be dominated by carbon rather than silicate, the CO ratio of the parent star, and therefore of the disk, must be much higher, above 1 by most models, significantly above 1 by some. The second condition is that the planet must form in a part of the disk where the temperature was high enough for the relevant chemistry to play out. In a carbon-rich disk at the temperatures corresponding to the inner rocky planet zone, the dominant solid grains that condense out of the gas are not silicates. They are carbides, in particular silicon carbide, which is a hard, dense ceramic mineral that on Earth is known as carborundum and is used in industrial abrasives. As the disk cools, additional carbon-bearing solids form, including graphite. By the time the disk has cooled enough for silicate-bearing grains to start condensing, in a carbon-rich disk, the silicates are a minority component. The bulk of the rocky material that ends up in the inner planets is carbon-based. The third condition is that, once the planet has formed, the high pressure of its interior must convert the carbon at the appropriate depth into diamond. This is, in fact, the easy part. Diamond is the stable form of carbon at pressures above about 30,000 times Earth's surface atmospheric pressure and at temperatures up to about 4,000 degrees Celsius. In the deep interior of a super-Earth, both conditions are easily met. Below a few hundred kilometers of depth in a carbon-rich planet, the carbon would naturally crystallize into diamond. The diamond would not, importantly, be the kind of perfect transparent gemstone you see in jewelry. It would be polycrystalline, opaque, possibly mixed with other minerals, possibly under such pressure that its physical properties are quite unlike the diamond we know on Earth, but it would be chemically and crystallographically diamond. The fourth condition, which is the one that ultimately killed the simple version of the story, is that the host star's measured carbon to oxygen ratio must actually be high enough to support the model. In 2012, the early measurements of 55 Cancri's chemistry suggested a CO ratio of about 1.1 or 1.2. That was high enough, just barely, to make the carbon-rich planet model viable. But the measurements were, even at the time, uncertain. The lines of carbon and oxygen in the spectrum of a star like 55 Cancri A are notoriously difficult to disentangle, and the systematics of different analysis methods can shift the result by 10 or 20%. The diamond model rested in 2012 on a stellar abundance measurement that was, by the most cautious astronomers' standards, not yet reliable enough to bet too much on. That is, in the end, what got the model into trouble. Part 7. The Walk Back. The first serious challenge to the Diamond Planet model came in 2013 in a paper by an astronomer named Johanna Teske at the University of Arizona and her collaborators. Teske and her team made careful new measurements of 55 Cancri A's spectrum, focusing specifically on the carbon and oxygen lines, with attention to the systematic effects that had, in 2012, made the original measurements uncertain. When they finished the analysis, the carbon-to-oxygen ratio of 55 Cancri A came out at about 0.78, not above 1, below 1. Very close, in fact, to the value of our own Sun. That single measurement, when it was published, more or less ended the simple version of the Diamond Planet story. If the host star's CO ratio is below 1, the disk from which the planet formed was oxygen-dominated, not carbon-dominated. The standard chemistry of planet formation produces silicate-rich grains, not carbide grains. The interior of a planet formed from such a disk, regardless of its bulk density, should be silicate-rich, not carbon-rich. Diamond in such a planet might exist in trace amounts. It would not be a major fraction of the planetary mass. Subsequent measurements by other groups confirmed the Teske result. A paper by an astronomer named Paul Erik Nissen at Aarhus University in Denmark in 2014 used a different analysis pipeline and came to a similar conclusion. The CO ratio of 55 Cancri A, by the best modern measurements, sits at around 0.75 to 0.8. Not far from solar, not above 1. There is a small but important detail about how stellar abundances are measured that is worth a brief explanation, because it tells you something about why the original 2012 numbers were uncertain. The carbon-to-oxygen ratio of a star is determined by measuring the strengths of specific spectral lines of carbon and oxygen in the star's spectrum. The lines, in absorption against the continuum of the star's light, indicate how much of each element is present in the photosphere. In principle, the measurement is straightforward. In practice, the lines of carbon and oxygen are notoriously difficult to work with. The carbon lines are, at the temperatures of a star like 55 Cancri A, weak and blended with other features. The oxygen lines are similarly difficult. The chemistry of the photosphere, which determines how much of each element is in atomic form versus locked up in molecules like CO, depends sensitively on the temperature and pressure structure of the photosphere itself, which is also being inferred from the same spectrum. The systematic uncertainties in the analysis can shift the inferred CO ratio by 10 or 20%, depending on which choices the analyst makes about line lists, atmospheric models, and continuum normalization. In 2012, the early measurements of 55 Cancri A's CO ratio came out high, possibly above 1. The Madhusudhan paper used these high values as the basis for its proposed carbon-rich interior model. By 2013 and 2014, with more careful systematic analysis, the CO ratio was being measured at substantially lower values, around 0.75 to 0.8, not above 1. Not different from solar in any dramatic way. The shift was not, in the technical sense, a contradiction of the original measurements. It was a refinement. The earlier numbers had larger systematic uncertainties than the original analysis fully appreciated. The newer numbers, with better systematics control, were closer to the truth. That is, in some sense, the most important sentence in this whole story. The diamond planet hypothesis was not falsified by some new and unexpected discovery. It was eroded by the gradual improvement in the systematic accuracy of an older measurement. The host star's chemistry, when measured more carefully, was less unusual than the early measurements had suggested. The unusual planet on the basis of an unusual host star became less unusual as the host star turned out to be less unusual than originally thought. Madhusudhan, when the new measurements came in, did not retract his original paper. He did, however, publish follow-up work that engaged carefully with the new abundance results. The picture he advocated in his later papers was more nuanced. Even if 55 Cancri A's bulk CO ratio is not above 1, he noted, the protoplanetary disk near the planet's formation location could have had a different ratio than the bulk star, due to chemical differentiation processes within the disk. There were specific physical mechanisms by which the inner part of a protoplanetary disk could become enriched in carbon relative to the bulk star, even if the bulk star itself was oxygen-dominated. So the diamond planet model was not entirely dead in his telling. It had simply been moved from a position of central plausibility to a position of one possibility among several. That, more or less, is where the diamond planet story sat for the next decade. The strong version of the hypothesis in which 55 Cancri A was a fully carbon-dominated world with a thick diamond mantle had been ruled less likely. The weak version in which trace amounts of carbon-rich material existed at depth was still on the table. The bulk density measurement was still consistent with multiple compositional models. The interior in 2014 and on into the 20-teens remained genuinely uncertain. Here is the thing I want you to sit with for a moment. The diamond planet story, in its strong form, was probably wrong. But the weakening of the hypothesis was not the result of a single decisive observation. It was the result of a slow accumulation of stellar abundance measurements, each of them refining the picture, each of them pulling the CO ratio of 55 Cancri A slightly closer to solar. The strong version of the story did not die in a thunderclap. It died in a series of cautious papers by careful astronomers, none of whom were trying to make headlines. The popular imagination, of course, did not entirely follow the walk back. Even today, on the internet, you can find articles describing 55 Cancri E as a diamond planet, with a confidence the science has not justified for at least a decade. The science has moved on. The popular telling, in many places, has not. Part 8. The day side, and what we measured next. With the diamond hypothesis weakened, the question of what 55 Cancri A is actually made of returned after 2014 to its original difficulty. The bulk density was high. The composition was constrained, but not pinned down. The interior could be iron-rich silicate with a slightly elevated iron fraction relative to Earth. It could be a stripped mantle world in which the planet's outer silicate layers had been blown away by stellar irradiation, leaving a denser core exposed. It could be some combination. The interior models by 2015 were genuinely degenerate. Multiple combinations of materials gave acceptable fits to the bulk density. Without additional information, there was no way to distinguish between them. The additional information started to come in slowly from observations of the planet's atmosphere and surface emission. The most informative of these came from a program of Spitzer Space Telescope observations led by Brice-Olivier de Maury and his collaborators in 2016. De Maury's team observed the planet across many orbits using Spitzer's infrared photometric capability and built up a phase curve of the planet's brightness as a function of orbital position. The phase curve, in principle, tells you how the planet's brightness varies with the side facing Earth, which in turn tells you about the temperature distribution across the planet's surface. The result was, in some ways, the strangest thing yet measured, about 55 Cancri A. The day-night brightness contrast was very large, suggesting a day-side temperature of around 2,400 degrees Celsius and a night-side temperature of around 1,100. That temperature contrast is consistent with a magma ocean on the day side and a much cooler, possibly partly solid surface on the night side, with very limited heat transport from one side to the other. So far, so consistent with what models would predict, but the phase curve also showed something that surprised the team. The hottest spot on the planet was not directly below the substellar point where the star is permanently overhead. It was offset by a substantial amount, and, more strangely, the offset, when observed across multiple orbits, varied. Sometimes the hot spot was east of the substellar point, sometimes it was west, sometimes the magnitude of the offset changed. The hot spot offset, when the original de Maury result came in, was particularly striking. On other tidally locked planets like HD 189733b, the hot spot is offset from the substellar point by about 30 degrees, in a direction that matches the predictions of standard atmospheric circulation models. The wind drags the hot spot eastward by an amount that depends on the wind speed and the radiative timescale of the atmosphere. On 55 Cancri E, the offset was both larger than expected and variable in time. In some observations, the hot spot was 40 degrees to the east of substellar. In others, it was much closer to substellar. In still others, the offset appeared to be in a different direction entirely. The pattern, when the team plotted it across many orbits, did not fit any of the simple steady-state circulation models. That kind of variability on a tidally locked planet is not what the simplest models predict. A tidally locked magma ocean should have a roughly stable temperature pattern with perhaps a slight wind-driven offset of the hotspot, but with the offset itself stable in time. Variability in the offset suggests something more dynamic. The leading interpretations when the team published the result were two. One was that the planet had an unusually variable atmosphere, in which the wind patterns shifted on timescales of weeks to months, redistributing heat in changing ways. The other was that the planet had ongoing volcanic activity, with episodic outgassing events that produced transient atmospheric features and shifted the apparent hotspot from one observation to the next. Either way, the picture was not a simple, steady state. The planet was, in some active way, alive. Here is the thing. Volcanic activity, if it is what is happening, has implications for the composition. A volcanically active planet is one whose interior is producing fresh material at the surface on a regular basis. The material that comes out in volcanic outgassing is determined by the composition of the deep interior. By measuring what comes out, you can, In principle, infer what is down there. The De Maury result in 2016 did not pin down the composition. It did, however, suggest that the planet was the kind of place where, with the right follow-up observations, the composition might eventually be measured directly. Part 9. JWST arrives. The follow-up observations, when they came from the James Webb Space Telescope. In 2024, in a paper in Nature, a team led by an astronomer named Renyu Hu at NASA's Jet Propulsion Laboratory used JWST's MIRI and NIRCam instruments to observe 55 Cancri E during multiple secondary eclipses. The team's observation strategy was carefully designed to maximize the planet's signal against the noise of the much brighter star. They used the secondary eclipse method, in which the planet passes behind the star, and the team measures the difference in total system brightness with and without the planet contributing. The difference, integrated over many wavelength bins, gives the planet's emission spectrum. The goal was to characterize the planet's emission spectrum in detail and to see whether the patterns in the spectrum matched the predictions of various interior and atmospheric models. The team was in particular looking for signs of a substantial atmosphere. What they found was unambiguous. The spectrum of 55 Cancri E showed clear absorption features consistent with carbon dioxide and carbon monoxide in the planet's atmosphere. Not a thin escaping envelope. A substantial atmosphere, possibly tens of bars of pressure at the surface, definitely more than enough to constitute a real atmosphere in the conventional sense. The result, when it was published, was a significant revision of the picture of 55 Cancri A. The planet, on the new evidence, is not a bare rock. It is a rocky super-Earth with a thick CO2 and CO atmosphere, possibly dynamically maintained by ongoing volcanic outgassing, possibly residual from the planet's formation, possibly some combination. That finding, when you sit with it, has consequences. A bare, rocky planet, if it had ever existed, would not have been able to retain any significant atmosphere over the planet's lifetime. The intense stellar irradiation at this orbital distance would have stripped any atmosphere away within tens of millions of years. The fact that the atmosphere is there today means that either the atmosphere is being constantly replenished, or the planet has retained much more volatile material than simple models would predict, or some combination of both. The most natural interpretation, given the variable hotspot, is volcanic outgassing. The planet's deep interior is producing CO2 and CO at a rate fast enough to compensate for atmospheric stripping. The atmosphere we see is, in this picture, a steady-state balance between outgassing and loss. Here is the part that complicates the diamond story even further. A carbon-rich interior, in the sense the Madhusudhan paper proposed, would not necessarily produce CO2 and CO atmospheres of the kind JWST detected. A carbon-rich interior, depending on how it interacted with the small amount of oxygen in the planet, might produce different volcanic outgassing chemistry. Carbon monoxide, yes, in some scenarios, but the specific balance of CO2 and CO that JWST measured fits more comfortably with a silicate-rich, oxygen-bearing interior of the kind we have on Earth than with a carbon-dominated one. The new atmospheric measurements, in other words, push the picture even further away from the diamond planet model. By 2024, the dominant picture of 55 Cancri A was no longer carbon-dominated at all. It was instead of a rocky super-Earth with a substantial volcanically maintained CO2 toll CO atmosphere, possibly with a magma ocean on the day side, possibly tidally locked, with an interior that, while perhaps slightly different from Earth's in proportions, was almost certainly silicate-rich and not carbon-rich. The diamond, by every measurement in our hands today, is probably not there. The Hu et al. Paper appeared in Nature in May of 2024. It was, by the standards of the field, a major result. The detection of a substantial atmosphere on a rocky exoplanet with characterized composition was something that very few teams had managed at all by that point. The fact that 55 Cancri turned out to host such an atmosphere, against earlier expectations that the planet might be a bare rocky body with at most a thin escaping envelope, was a meaningful update to the field's picture of what hot, rocky planets look like. The Hu paper, when it was published, also had implications for our understanding of how the planet's atmosphere is replenished. A bare, rocky planet at this orbital distance, with no atmospheric replenishment, would lose its atmosphere within about 100 million years to the combination of stellar radiation and stellar wind stripping. The fact that the atmosphere is there now on a planet that has been around for billions of years requires either a very efficient replenishment mechanism or a very large initial reservoir of volatiles, or some combination. The leading interpretation which the Hu paper itself favoured is volcanic outgassing. Carbon dioxide and carbon monoxide in the chemistry of a magma ocean are produced naturally by the equilibrium between molten silicate and dissolved volatiles. As the magma circulates, gases bubble out of solution and rise into the atmosphere. The rate is, on the best estimates, sufficient to maintain the observed atmospheric mass against the rate of loss to space. That picture of a planet whose atmosphere is being constantly replenished by volcanic outgassing from a global magma ocean is one of the more dynamic pictures in modern exoplanet astronomy. Earth's atmosphere is also, in some sense, replenished by volcanism, but on much longer timescales. Earth's atmosphere is roughly stable over millions of years. 55 Cancri-E's atmosphere may be turning over much faster, on timescales of perhaps 1,000,000 years or less, with the gases we measure tonight being, in a real sense, gases that were locked in the planet's deep interior less than 1,000,000 years ago. The atmosphere is not just present. The atmosphere is, in a slow, geological sense, alive. Part 10. What 55 Cancri probably actually is. If you take everything we have measured about 55 Cancri and you put it together into the most likely picture, what do you get? The planet is, by the best current evidence, a rocky super-Earth in a 17-hour orbit around a sun-like star. It is tidally locked. Its day side is at about 2,400 degrees Celsius, hot enough to keep a global magma ocean of liquid silicate. Its night side is much cooler, at around 1,100 degrees, although that is still hot enough to keep some silicates partly molten and most metals liquid. The interior is silicate and iron in proportions roughly similar to Earth's, with perhaps some adjustments to account for the slightly higher bulk density. The atmosphere is dominated by carbon dioxide and carbon monoxide, with possibly trace amounts of other species, and is being actively replenished by volcanic outgassing from the dayside magma ocean. The hotspot is variable, suggesting active atmospheric or surface dynamics on timescales of weeks to months. That picture, when you read it carefully, is recognizable. It is the picture of a super-Earth-scale Venus, in some sense. A hot, dense, rocky world with a substantial CO2 atmosphere, geologically active, perhaps on its way to or from various states of greenhouse maintenance. Venus, in our own solar system, is much cooler than 55 Cancri, but it shares many of the same general features. CO2-dominated atmosphere, volcanically active, no surface oceans of water, although Venus does not have a magma ocean either. The two planets, in some loose sense, occupy related parts of the same physical regime. What is different, of course, is the temperature. 55 Cancri E's day side is hot enough that the rock itself flows. That is something Venus does not do. The chemistry at 2,400 degrees is not the chemistry of Venus's 700-degree atmosphere. The dynamics of a global magma ocean are not the dynamics of any place in our own solar system. So 55 Cancri E is, in some important sense, a new kind of world. Not a diamond planet, but not Earth, and not Venus, and not Mercury, something genuinely without close parallel in our local catalogue. The interior, beneath the magma ocean, is the part we know least about. Some of the deep interior models still have room for unusual compositions. There may be carbon-rich layers at intermediate depths between the silicate mantle and the iron core, although the carbon would not be the dominant component. There may be hydrogen-bearing minerals at depth, contributing to the high density. There may be features we have not yet thought to look for. The interior of 55 Cancri E, even after 20 years of intense study, has parts we genuinely have not yet pinned down. That is, in some sense, the appropriate state of knowledge for a planet 41 light-years away that is too small and too dim to image directly, that has a surface we can only infer from the way it absorbs and reflects starlight, and that we have no way of visiting in any practical sense. We know a lot about it. We do not know everything. The composition, 23 years after the planet was discovered, is still something we are working out. Part 11. The honest position. Here is the genuinely complicated state of knowledge about 55 Cancri E, as best as I can reconstruct it from the literature. I am not saying that 55 Cancri E is made of diamond. The evidence, particularly the host star's chemistry and the JWST atmospheric observations, makes that interpretation unlikely. I am not saying the diamond hypothesis was a bad idea. It was a good hypothesis in its time that made testable predictions and led to better measurements that eventually weakened it. I am not saying we know exactly what the planet is made of. We do not. What I am saying is something quieter than any of those. What I am saying is that the planet is, by our best current evidence, most likely a hot, rocky super-Earth, with a silicate iron interior similar to Earth's in broad outline, but with a higher density, with a substantial CO2-CO atmosphere, with a global magma ocean on its tidally locked day side, and with ongoing volcanic activity that produces variable surface and atmospheric features. That is the consensus picture. It is consistent with all the observations we have made. It might be wrong. Future observations, particularly with JWST and with the upcoming aerial mission, may reveal features that change the picture. But the picture, as it stands tonight, is the most defensible position. That position is, in its way, less dramatic than the Diamond Planet headline. A rocky super-Earth with a CO2 atmosphere is not a sensation in the way that a diamond planet worth $26 nonillion is. The popular imagination has, to some extent, moved on from 55 Cancri A for that reason. The real planet, when we measured it more carefully, turned out to be more interesting in subtle ways and less interesting in headline ways. That is a pattern that recurs throughout exoplanet astronomy. The first dramatic claim is often partially walked back. The slower, more careful work is usually less catchy. The audience, on the whole, drifts to the next dramatic claim. The patient researchers, on the whole, stay with the original target and keep refining the picture. 55. Cancri E is, in some sense, an object lesson in this kind of patience. The planet was discovered in 2004. The diamond hypothesis was published in 2012. The walk-back papers came in 2013 and 2014. The first phase curve was in 2016. The JWST atmospheric observations were in 2024. From discovery to the current consensus picture, 20 years passed. That is, on the time scale of a human career, a substantial fraction of a working life. The astronomers who started studying this planet as graduate students in the mid-2000s are, by now, established faculty members. Their students, in turn, are starting their own careers, working on the same planet from a slightly different angle. The continuity across decades is part of the work. Nobody in this field expects to finish the story. Everybody expects to add a chapter, or sometimes a paragraph, to a story that will continue long past their own retirement. The work is collective, in a way that does not always come through in the press releases. The press releases give credit to specific people for specific results. The story, beneath the press releases, is being written by hundreds of contributors, none of whom owns it. That is, when you sit with it, a deeply unusual relationship to have with one's work. The astronomers who study 55 Cancri E know, going in, that they will not be the ones who definitively settle the question of what the planet is made of. They will contribute one result or two, or in some cases a series. Other people, working on the same planet years later, will contribute the next round of refinements. The picture, at any given moment, is a snapshot of a slowly moving consensus. The consensus at any given moment is the product of a long collaborative conversation that no individual conducts. The work is, in some sense, more interesting because of this distributed quality. Nobody can take full credit. Nobody is, by the same token, fully responsible for getting it wrong. The community absorbs and processes the data on its own slow timescale, and the picture improves, paper by paper, decade by decade. Here is something I want to be honest about. The Diamond Planet story, even though it was probably wrong, did real scientific good. It motivated careful follow-up measurements of 55 Cancri A's chemistry, which produced more reliable abundance estimates that have since been used in many other contexts. It pushed atmospheric retrieval techniques to new levels of precision, which have benefited many other planets in subsequent years. It demonstrated, very publicly, that serious scientific propositions about the interiors of distant worlds could be made on the basis of the data we now have. The fact that the specific proposition about 55 Cancri E turned out to be probably not quite right does not undo any of that. The story was, in its way, useful. The result that emerged from the careful follow-up is better than the result that the original press cycle promised. That is, in the end, exactly how science is supposed to work. Part 12. What it is actually like there. I want to spend the next few minutes building a picture in your mind of what 55 Cancri E probably actually is, in physical terms, with the level of detail that the current models support. This is the closest I can get in words to taking you there. You are arriving in the upper atmosphere, somewhere on the day side, near where the star is permanently overhead. The atmosphere around you is mostly carbon dioxide, with a substantial fraction of carbon monoxide and trace amounts of various other species. The pressure, at the level where you have arrived, is several bars, possibly a few tens of bars depending on which atmospheric model you trust. That is several to many times Earth's surface atmospheric pressure, but well within what would be physically tolerable to a hypothetical observer. The atmosphere is hot, at your altitude perhaps 1500 degrees Celsius, hot enough that none of the materials of any spacecraft we have ever built could survive there for more than a very brief time. The temperature, more than the pressure, is the dominant constraint on what is possible. Above you, the star takes up a vast portion of the sky. Its angular diameter is about 20 times the apparent size of the Sun from Earth. Its color is a deep yellow-orange, slightly redder than our own Sun, although the temperature gradient through the atmosphere may shift the apparent color somewhat by the time the light reaches your altitude. The star does not rise, it does not set, it does not move, it is in your sky, permanently in the same position, slightly past, directly overhead, if you are in the right longitude. The whole world, beneath you and above you, is illuminated by a permanent dim red-orange noon. Below you, through the atmosphere, the surface is, almost certainly, an ocean of molten rock, liquid silicate, at temperatures of about 2,400 degrees Celsius. The surface itself is, in any conventional visual sense, glowing. The thermal emission of the magma is in the visible spectrum. The rock, at that temperature, is incandescent, the colour of a piece of iron in a forge after the smith has been working it for an hour. The surface, when you look down, is a vast molten plain, with possibly some convective patterns visible as slightly cooler, dark patches drifting on the otherwise glowing background. The patterns on a global scale are dynamic. They move on time scales of hours to days. You can, if you watch carefully, see the magma ocean breathing. The wind in the atmosphere is moving from the day side toward the night side. The exact speed is uncertain, but the temperature gradient between the day side and the night side is of order 1,000 degrees, which drives substantial atmospheric circulation. The wind speeds in the upper atmosphere are likely several hundred miles per hour at minimum, possibly much higher. The wind carries with it vaporized silicate and other heavy elements blown off the dayside magma ocean. As the wind cools, in its journey toward the terminator, some of these heavy elements condense. They form on this planet a different kind of weather than what we saw on HD 189733b. The clouds here are different, the chemistry is different, but the basic principle of upper atmospheric condensation driven by the day-night temperature gradient is the same. The view downward from your altitude is dominated by the magma ocean. The ocean is, by every model that has been done, vast. It covers, in steady state, the entire day-side hemisphere of the planet. There are no continents, no islands, no shallow shelves. There is just the global pool of liquid silicate, breathing slowly with convective patterns, glowing red-orange against the underlying darkness, with patches of slightly cooler material drifting on the surface like dark ice flows on a fiery lake. The patches, over the course of hours, move, they merge, they split apart. They are dragged by the underlying currents, by the wind from above, by the slow rotation of the convective patterns within the magma itself. The ocean, watched from your altitude, is alive in a way that is genuinely unlike any ocean Earth has ever had. Earth's oceans are, by comparison, almost still. The magma ocean of 55 Cancri E is in continuous, visible, observable motion. If you let yourself drift with the wind, you would be carried, over the course of perhaps a few hours, toward the day-night terminator. The terminator is the edge of the day side, where the temperature gradient is steepest. Crossing it, you would feel in some sense the planet's pulse most strongly. The atmosphere at the terminator is condensing material onto the cooler night side. Fresh outgassed gases rising from the day-side magma ocean are being carried in the upper atmospheric current toward the terminator and beyond. The whole boundary is, in effect, where the planet's climate breathes. On the night side, the picture is different. The magma ocean is, on the night side, possibly partially solid. The temperature, around 1100 degrees, is at the lower edge of what keeps silicate liquid. Some of the surface on the night side may have crystallized into a thin, solid crust. The crust would not be stable on long time scales because the magma below would, on the day side rotation, eventually be carried back into the higher temperature regime. But on the night side surface, in steady state, there may be patches of solid rock drifting on a slow magma current like ice flows on a slow lake. The atmosphere on the night side is cooler. Some of the components that exist as gases on the day side condense on the night side into clouds or possibly liquid layers. The chemistry is, again, different from anything we know. There is, in the volume of cooler atmosphere on the night side, a kind of strange precipitation, possibly of various carbon compounds, possibly of silicates, possibly of ions and condensed metals. The exact nature of this precipitation is not yet settled by observations. It is, in the models, present in some form. The night side of the planet is, in a real sense, a permanent slow rain. There is one more feature of the experience that I want to add because it is one of the more remarkable aspects of magma ocean planets that does not always come up in the popular accounts. The day-side magma ocean in steady state is not chemically uniform. Different elements with different boiling points exist in different proportions, at different depths, and at different temperatures across the surface. Iron, which boils at lower temperatures than silicate, may be enriched in the upper layers of the magma ocean near the substellar point, where the temperature is highest. Aluminium, magnesium, calcium, and other rock-forming elements may be enriched at intermediate temperatures. The chemistry, as you move from the substellar point toward the terminator, gradually shifts. The magma at one location is not, in the strict sense, the same magma as the magma 5,000 kilometers away. Each region has its own proportions, set by the local temperature and the slow lateral mixing of the ocean. That kind of chemical heterogeneity in a global magma ocean is hard to model in detail. The dynamics of liquid silicate at extreme temperatures with the chemistry of multiple elements interacting in a tidally locked configuration with strong day-night gradients is a problem that even the best supercomputers struggle with. We have by now some preliminary models that try to capture the basic physics. We do not have by any reasonable standard a fully detailed picture. The day side of 55 Cancri E on the time scale of the next few decades of model development and observation is going to be one of the central testbeds for our understanding of how magma oceans actually work. On planets where they are the dominant surface feature, that is, as best as we can construct it tonight, what 55 Cancri E probably actually is. A magma ocean planet with a thick CO2 atmosphere, with global circulation driven by the day-night gradient, with active volcanic outgassing, with a cooler night side that may have a partly solid surface and condensing precipitation. Not a diamond planet. Something stranger, in its way, than any of the simple models would have predicted. Something genuinely new in our growing catalogue of small worlds outside our own solar system. Part 13. The honest scale of what we do not know. Here is where we step back for a moment from the specifics of 55 Cancri E and think about what this single planet story tells us about the broader project of understanding planets around other stars. We have, over the past 30 years, gone from knowing about no exoplanets at all to having confirmed thousands. We have measured atmospheres of dozens. We have characterized a handful, like 55 Cancri E and HD 189733b and K2 18b and WASP 12b, in extraordinary detail. We have built, on the basis of that data, an emerging picture of the diversity of planetary systems in our local galactic neighborhood. The picture is rich. The picture is, by every measure, more interesting than what we expected when we started. It is also, in important ways, incomplete. The Diamond Planet story, in its arc, from striking hypothesis to slow walkback, is a small example of a much larger pattern. We are in this field frequently in the position of making bold initial claims about distant worlds on the basis of the limited data we have, and then refining or revising those claims as more data comes in. That pattern is not unique to 55 Cancri E. It applies to almost every planet whose properties have been studied for more than a few years. The early measurements have larger uncertainties. The early models have wider parameter spaces. The early stories are more striking, partly because the data does not yet rule out the more striking possibilities. As the data gets better, the parameter space narrows. The stories become more precise, often less dramatic, sometimes more interesting in subtler ways. There is a feature of this kind of work that I find genuinely beautiful, which is that the science improves on its own previous claims in public, in the open literature, with no institutional embarrassment about doing so. The Diamond Planet hypothesis was published in 2012. The walkback papers were published in 2013 and 2014. The original authors did not protest. The new authors did not gloat. The whole field, as a community, simply absorbed the new results and updated its picture. The literature, when you read it across the decade, shows a slow conversation in which the position evolves. Nobody is shamed. Nobody is forced to admit defeat. The picture just gets sharper, paper by paper, until what remains is what the data actually supports. That is, in many ways, the closest thing science has to a model for how human beings might collectively change their minds. We are, all of us, listening to a long story that the universe has been writing for billions of years, and that we have only recently learned how to read. The first chapters in our reading have been somewhat dramatic, because we have not yet had the calibration to distinguish the dramatic from the merely interesting. As we get better at reading, the story becomes more nuanced. The diamond planets become magma ocean planets with CO2 atmospheres. The biosignatures become tentative spectral features awaiting confirmation. The Earth-like worlds become, on closer inspection, something not quite like Earth. The whole catalogue is, in some sense, more interesting in detail than it was in the early summary headlines. We are still early, the instruments are still being built. JWST is in the middle of its mission. Ariel is launching in 2029. The Habitable Worlds Observatory will not fly until the 2040s. The story, in the slowest possible sense, is just beginning. The chapters we have read so far are, by any reasonable accounting, the first few. The full book will take generations to write. We will not be alive to read most of it. That is, when you sit with it, an unusual kind of work to be doing. Most fields of science have the comfortable expectation that, within a working career, the questions you start with will be at least partially answered. In exoplanet science, the questions are slow. The answers, when they come, often come decades after the questions were first posed. The scientists who proposed the Diamond Planet model in 2012 have, in the years since, lived through its weakening and its refinement. The scientists who will eventually settle in some final way the question of what 55 Cancri E is actually made of may not yet be born. That is the kind of timescale this work runs on. The patience is, in a way, the work itself. There is a question sometimes asked at the edges of all this work that I have not yet addressed. Why are we doing it? Why are we spending the budgets of major telescopes and the careers of thousands of researchers on the chemistry of small, dense planets 41 light years away? The honest answer, when you talk to the people who have given their lives to this kind of astronomy, is rarely the practical one. It is rarely about national prestige. It is rarely even about the abstract glory of scientific achievement. The most common answer, when pressed, is something much simpler. They want to know. They want to live in a universe whose details they can sit with, that they can describe accurately, that they can pass on to the next generation in a more refined form than they themselves received it. The work is, in a deep sense, an act of curiosity that does not need to justify itself to be worth doing. That kind of pure curiosity, when it is allowed to operate at the institutional scale that modern astronomy requires, produces results like the Diamond Planet story. The story, even in its eventual partial walkback, is a story that human beings collectively wanted to know. The original question of what 55 Cancri A is actually made of is a question that nobody has any practical use for. There is no application. There is no policy implication. There is no industry that depends on the answer. But the question is, in itself, worth asking, because asking it produces a more complete picture of the kind of universe we live in. The picture, when you put it all together, is one of the more remarkable products of modern human civilization. Part 14. Coming Home. We did not set out to find a diamond planet. We set out to find planets of any kind around other stars. In the early 1990s, when nobody knew if any other stars even had planets at all, the discovery of 51 Pegasi b in 1995 opened the door. The decades since have seen the catalogue grow from 1 to several thousand, with detailed characterization now possible for hundreds of them, and the techniques continuing to improve. 55. Cancri A was, in that sequence, just one more discovery among many, until 2012 when, briefly, it became something else. A hypothetical diamond planet, the most expensive object, by some headline metric, in human imagination. It is no longer that. It is something more interesting in some sense and less dramatic in others. A magma ocean world, a rocky super-Earth with a thick atmosphere of carbon dioxide, a planet whose interior we are still working out, a planet whose hot spot wanders, suggesting active volcanism on timescales we can almost watch. A real planet with real chemistry, with real weather, with real geological activity, 41 light years from where you are listening tonight. The constellation Cancer is in the spring sky in the northern hemisphere between Gemini and Leo. Cancer is one of the dimmest constellations in the zodiac. Its brightest star, Beta Cancri or TARF, has a magnitude of about 3.5, which is a comfortable naked-eye object on a moderately dark night, but not nearly bright enough to dominate the sky. 55. Cancri itself is fainter, magnitude 6, just at the limit of unaided eye visibility. If you go out tonight on a clear evening and find Cancer in the sky and look very carefully at the right point in the constellation, you can see the star whose innermost planet we have spent this evening with. The star is called 55 Cancri A. It is, by every important measure, a near twin of our own Sun. It is 41 light years away. The light reaching your eye tonight left that star in the late 1980s. Around that star, every 17 hours and 44 minutes, a small, dense super-Earth is making a hot lap of its Sun. The lap is invisible to you. The planet is far too small and too close to its star to be seen from Earth without specialized instruments. But the planet is there, its day side is at this moment glowing, its atmosphere is at this moment full of carbon dioxide and carbon monoxide. Its hot spot is at this moment in some position that may or may not be where the simplest models would predict. Its volcanoes, if there are volcanoes in any meaningful sense, are doing whatever they are doing. The whole permanent system of magma and gas and slow rain is operating on its own clock, regardless of whether anybody is watching. We thought, for a brief and dramatic moment in 2012, that this planet was made of diamond. We were probably wrong. We were, by the standards of the science that came after, well-meaning, but not quite right. What we have in place of the diamond is a more complicated picture, a picture in which the planet is made of materials we know well, in proportions we are still working out, with weather we can begin to model, with an atmosphere we have just started to characterize, with a deep interior that we genuinely do not yet understand. You can let it go for tonight. The planet is doing its slow, patient work, regardless of you. The magma ocean is breathing. The atmosphere is circulating. The CO2 is being replenished somewhere by some volcanic vent or by some other process. The 17-hour year is at this moment ticking through itself, lap after lap, the way it has been ticking for billions of years. Nothing about it requires your attention. The diamond, if it is there, is somewhere very deep, far below anything we can see, in trace amounts that the bulk measurements cannot yet rule in or out. The diamond, if it is there, is a curiosity of the deep interior, not the dominant feature it once seemed. The planet, in the catalogue we have tonight, is not a diamond planet. It is, instead, the planet we thought was made of diamond. The thinking was good. The walking back has been honest. The picture, by the standards of modern exoplanet science, is the best picture we have at the present moment of one specific, small, dense world 41 light years away. That is enough for tonight. Good night. Sleep well. The magma ocean is still breathing. The atmosphere is still doing its slow circulation. The planet is exactly as we left it, not made of diamond, not quite made of anything else we can fully name yet, but very real, very persistent, and very patient with us as we work out the rest of its story. There is a final thought worth leaving you with before sleep. The light from 55 Cancri reaching Earth tonight left that star around the late 1980s. Many of the astronomers who would later build their careers around this planet were, in that era, still in graduate school, or still in undergraduate programs, or, in some cases, not yet old enough to be thinking about science at all. The photons that are arriving tonight, with their tiny information about the planet's atmosphere encoded in the absorption lines, were already on their way before the field of exoplanet astronomy existed in any practical sense. The mail was being sent before there was a delivery infrastructure. By the time the mail arrived, the infrastructure had been built. The synchronization between the photons traveling and the technology being developed is the kind of accident that, in this kind of work, makes the modern era possible. The light continues to arrive. We continue to learn. The story continues somewhere in Cancer, every 17 hours, regardless of what we know or do not know about it tonight. There is a small symmetry to the story I want to leave you with before we let it go for tonight. The Diamond Planet, as a hypothesis, was a story about something hard and crystalline at the heart of a distant world. What we now think is there instead is something molten, a magma ocean, liquid rock glowing in the dark, breathing slowly under the steady illumination of a star that does not move. The shift from diamond to magma is in a way a shift from the imagined to the real. The diamond was an elegant idea. The magma is the actual chemistry. The story, when you trace it from 2012 to today, is a story about hard, crystalline guesses gradually giving way to soft, hot reality. The reality, in some sense, is more interesting than the guess. It is also harder to capture in a single headline, which is part of why the popular telling, even today, is still half stuck on the diamond version. You can let the planet go for tonight. The magma is still flowing, somewhere in Cancer, around a sun-like star you cannot quite see. The CO2 is still being outgassed by some volcanic vent somewhere on the day side. The hot spot is still wandering by some amount in some direction, on a schedule we have not fully decoded. The planet is still there, doing what magma ocean planets do on its 17-hour clock, regardless of whether anybody is watching. Good night, again, sleep gently. The planet is still there. The diamond, if there is any, is somewhere very deep, in trace amounts under so much pressure that it would not, in any conventional sense, look like diamond at all. The magma is breathing. The atmosphere is being replenished. The crab, in the spring sky, is doing what crabs in old constellations do, which is sitting quietly while the universe goes on around it. Sleep well. The light continues to arrive. There is one final image I want to leave you with. The host star, 55, Cancri A, is just bright enough to see with the naked eye on a dark night. Magnitude 6. Right at the limit of what a human eye in good adaptation can resolve. If you go outside on a clear night in a place reasonably free of light pollution, and you find the constellation Cancer in the spring sky, and you look very carefully at the right point in the constellation, you can see it. The light reaching your eye at that moment is the light that left 55 Cancri A around the time the Cold War ended. That light has been travelling through the empty space between us and that star while the entire field of exoplanet astronomy was being built. The photons started their journey before anybody on Earth knew that other stars had planets. They are arriving tonight in a world where we know that planet with the level of detail this story has covered. That synchronization between the photons and our preparation is one of the small accidents that makes this kind of evening possible. We are alive on this planet in the first generation in human history that knows what is around 55 Cancri A. We will not be alive in the generation that finally settles in some final way what 55 Cancri E is actually made of. But we are alive in the generation that has measured its color, mapped its hot spot, characterized its atmosphere, and walked back, in a slow and careful way, the diamond hypothesis that briefly captured the public imagination. That is, for one generation, plenty. Good night. One more time. The crab is in the spring sky. The faint star is in its catalogue position. The planet, whose composition we are still working out, is making its 17-hour lap around its sun, with its magma ocean breathing under its CO2 atmosphere, with its diamond, if there is any, somewhere very deep, in trace amounts under so much pressure that it would not look like diamond at all. The story is tonight exactly where we left it. The patient work continues. The light, faithful and steady, keeps arriving. Sleep gently. The story is in good hands. The picture, on every careful measurement, gets a little sharper. The magma is still flowing. The atmosphere is still circulating. The hot spot is still wandering. The light is still arriving, 64 years late, on whatever instruments happen to be pointing at the right patch of sky tonight. The story continues, the reading continues, the picture, one observation at a time, gets sharper. Good night. The planet is patient, the star is patient, the light is patient. The story, as always, takes longer than any individual evening, longer than any individual lifetime, longer than any individual generation. We are all in this kind of work, contributing one quiet brick to a wall that has been under construction for centuries and will continue, brick by careful brick, long after we are gone. Sleep well.